Hi, everybody. Today, we're going to be taking a look at Taylor and Maclaurin's series, which is an extension of the power series we talked about recently. Definitely need your notebook. We're going to get a couple of new equations onto our cards. So you can wait until we get into class to put them on the cards, or if you have some extra cards, you'll see the spots where I'll tell you to do that. Make sure that you're pausing when I'm asking you to pause and maybe try on your own. We definitely will talk about this over the next couple of days in class, and please, please, please make sure you're trying to practice problems. This is not a spectator sport. We got to make sure that we know how to do these problems and know where we're going to run into some questions by working through the equations. So with Taylor's series, obviously it's named after the mathematician Brooke Taylor. He, once again, like most mathematicians, did some work in a variety of different areas. But it was his work with James Gregory, where he was working through series. Gregory had already been working on some series, but Taylor was the first to publish some of this information, so he gets the credit. All right, so here's our goal, and we kind of saw this with our last lesson. Our goal is to have a power series, or this infinitely long polynomial equation that looks like or mirrors or mimics the behavior of the function that we're trying to approximate. So again, we're taking hard functions, transcendental functions like trig functions, logarithmic functions, and trying to come up with polynomial functions that mimic them, because polynomial functions, when you substitute in a value, all you got to do is multiply and add, subtract, and divide. And so those are easy operations. So I almost, again, think of these as we're trying to create tangent curves, because there's only going to be one point where the two touch, and you can see with the animation here that it's going through some different powers. So we're starting out here with a linear or constant linear, quadratic, cubic, quartic, quintic. And so as you add more and more powers, we get more and more curvature that starts to match the blue functions. So then I can use the red polynomial to make my approximations. I don't know if we're going to make any approximations today. We're just going to try to come up with what is a really good equation of that red curve, that polynomial curve, to match my given function. Now again, some of these will be on closed intervals like we talked last time, but some of them will be on open intervals, and we'll get a glimpse into some of them here today. So this is our goal. We want to come up with a polynomial function. And so our goal really is to figure out what are these coefficients, what are these a values, to then create a polynomial that looks like a given function. And let's take the function ln of x plus 1. Natural log is really hard to evaluate at certain values, but if I was able to get a polynomial to approximate it, that's easy to figure out polynomial values. And we're going to center this at 0. The center point is going to be the shared point between both the function ln of x plus 1 and the polynomial. And the way that we're going to do this is that we're going to want, obviously, the two functions to be equal to each other at 0, because that'll be their quote-unquote point of tangency, the one place where they will touch. But then if I make the first, the second, the third, and the fourth, and multiple derivatives the same, well, then that's going to start to control where they increase and where they decrease, and their concavity and things like that. So that's going to be our goal, is to get some few of the derivatives to be equal to each other, the polynomial and the function itself. So let's go through and do that. We're going to do this pretty systematically. So you want to be following along here. So I got my polynomial that I want to figure out all these 5 coefficients for, a sub 0 through a sub 4, and I want it to match the ln of x plus 1, at least within a certain interval of convergence. And for this one, it'll be between -1 and 1, which we'll discuss a little bit later. So here we go. We're going to take my function and evaluate it at 0, and I know that that is equal to 0. Well, I want now the polynomial to have the same value of the function at 0. So here's my polynomial, and I want its value at 0. Well, its value of 0 will get rid of all these x terms, and I'll just have a sub 0. So therefore, I want the polynomial and the function to be equal to each other, so therefore, a sub 0 is 0. I just figured out my first term. So that'll cause the two functions to be touching and equal to each other. If I move too fast through some of this, make sure you're pausing as we're going through. All right, so now let's make sure that the first derivative is equal for both. So here's my first derivative, easy derivative, and I'm going to evaluate it at 0. And so at 0, it turns out to be 1. So now I'm going to take my first derivative of the polynomial, which is really easy. It's a whole bunch of power rules. And I'm going to evaluate it at 0. And it at 0, once again, gets rid of all these x terms, and I'm just left with a sub 1. And so in order for the first derivative of the function at 0 and the polynomial of the function at 0, derivative at 0, I want them to be equal to each other, so therefore a sub 1 is 1. And we're going to keep going. Second derivative. Now be careful here. My derivative would have had to, in order to take this derivative, I'm going to rewrite this as 1 plus x to the negative first. So it's a power rule, chain rule problem. So there's my second derivative. At 0 is negative 1. Second derivative of the polynomial. At 0, the second derivative of the polynomial is 2a sub 2. So now I want both the function's second derivative and the polynomial's second derivative to be the same in order for these functions to kind of look like each other. So when I set them equal to each other, I get a sub 2 is equal to negative 1/2, setting them equal. If you think you kind of see the pattern going on here, why don't you continue? See if you can go and get a sub 3 and a sub 4 if you want to pause me now and try that. Second derivative after a power rule again. Or sorry, third derivative. Third derivative at 0 is going to be 2 for the function. Third derivative of the polynomial just keeps easy power rules here. So at 0, it's 6a sub 3. So therefore, a sub 3 must be 2/6 or 1/3. Yeah, we could reduce this, and you'll see why in a minute why I'm not going to reduce it. But yes, you can say it's 1/3. Fourth derivative. Now remember, when we get higher order derivatives, we don't keep putting tick marks. Now we put them in parentheses. So there's my fourth derivative, another power rule, chain rule. Fourth derivative at 0. Fourth derivative of the polynomial. Fourth derivative of the polynomial at 0. I'll set them equal to each other, so therefore a sub 4 is negative 6/24. Yes, it's negative 1/4. But again, in a second, you'll see why I don't reduce. So let's put them all together. Here we go. Putting all those coefficients in there, this polynomial will look very much like the ln of x plus 1. And you can check it on your calculator. If you pause me here, go ahead and put that into your calculator. Or actually, you might want to simplify it. This is if you actually reduce the fractions. So graph both of these at the same time, and you'll see that they should be pretty close to each other, and they should be actually touching at 0, 0. They both share that same point. Now beyond that, they're going to be really close, but not touching. But you can see, at least between negative 1 and 1, I've got a pretty good approximation. So this polynomial, the red, is really acting really well like my natural log function, natural log of x plus 1, shifted to the left one. So it's a really good. So then if I wanted to figure out the natural law or the function at 3, well, that means I've been trying to figure out the ln of 4. If I put 3 into there, well, all I would have to do is put 3 into my polynomial and evaluate it. Actually, I shouldn't say that because putting in 3, they're not going to be really close. I got to stick to a value between negative 1 and 1, so like 1/2. If I wanted to find the value of the function at 1/2, I would be evaluating the ln of 1.5. And so I would just be putting 1/2 into my polynomial. Hope that makes sense. Zooming in and you can see it's really, really good. But again, only touches at that one point at 0, 0. So these are like tangent curves. So is there another way that I could have figured this out? This seems pretty tedious, and we will use this as a method. But didn't we know what the power series for this was? Yeah, this was the geometric series where a is 1 and r is negative x. Do you remember that? So therefore my first term is 1, and then I'm multiplying by negative x times negative x times negative x. So why did I focus on 1 over 1 plus x? What's that relationship to the ln of x plus 1? Why did I do that? Well, the derivative in the natural log of x plus 1 is 1 over x plus 1, or 1 over 1 plus x. Don't let that throw you off. So what do I got to do here? Yeah, I got to anti-differentiate. So if I anti-differentiate the function, That means I got to anti-differentiate the polynomial, which I'm doing here, easy power rule. So therefore, I can now say that the antiderivative, which is the ln of 1 plus x, gives me this power series, which is what we just found a minute ago. So again, we might not want to actually create these every time through those multiple derivatives. We might want to find other series that I've already established and relate to those. So let's look for some patterns here. If I didn't reduce this, that's why I didn't want to reduce it, I can see up in the numerator this 1, 1, 2, 6. If you remember, those were the derivatives of the function, the higher order derivatives of the function itself. These denominators came from over on the polynomial side. They came from manipulating the polynomials. So it's always going to be a 2, always be a 6, always be a 24. Well, if you know anything about those numbers, 2, 6, and 24 and how they came about from those powers kept coming down and multiplying. Power came down and multiplied. So it was like building these higher and higher powers based upon factorials. This 24 was a result of the 3, the 2, and the 1 that came down before with those power rules that preceded it. So all of my polynomials with their higher order derivatives all fall into this pattern, no matter what the original function was. So I'm always going to fall into that particular pattern, and this is what is called a Maclaurin series. So Maclaurin series is a specific power series that's generated centered at 0, specifically at 0. So that polynomial will have the terms f of 0 plus f prime of 0 of x, and so on and so forth. Now, if you look carefully here, I've kind of left out some terms, so if it's maybe easier for you to see, there's technically an x to the 0 term here over 0 factorial. And 0 factorial is 1. Here's my x, or x to the first, over 1 factorial. So if you look carefully, it's the second derivative with the second power with the second factorial, 2 factorial. Third derivative, x cubed, 3 factorial. So it's really easy to kind of see what's going on here. So we want to make sure that we get this onto a note card, Maclaurin series, and then on the other side, the actual generation of the series. Okay, but what if I don't want to be centered at 0? Well, it's as easy as what we've been doing for years in shifting or translating polynomials to the left and the right. I got to just shift it by some value of x. So if I want to go to somewhere a center other than 0, like in that other earlier problem where I wanted to maybe evaluate it at 3, I might need to shift over so I get that interval of convergence to be somewhere near the value I'm trying to approximate. So now instead of taking all of the function values and its successive derivatives at 0, I'm going to do it at a. And now that I'm shifted over at a, where I want all those derivatives to be the same, now I've got to, instead of writing x, x minus a. That'll show the shift. This is the general Taylor series. A Maclaurin series is just a very specific form of the Taylor series where it's centered specifically at 0. Once again, I don't have the terms written here, but there'll be an x to the 0 over 0 factorial for that first term. And here is first power over 1 factorial, so you can see the pattern with the 2 squared and the 2 factorial, third derivative, third power, 3 factorial, and so on and so forth. So this also needs to get onto a note card. If you're going to remember 1, it's the Taylor series. But we're going to memorize some common Maclaurin series because we're going to be using them to do some comparisons. So make sure you have this down, and we'll take a look at the cosine function. So let's see if we can come up with a polynomial function to approximate the cosine function. Again, cosine of like weird angles is kind of difficult to do, but if I can write a polynomial, I can use that to just generate some cosine values because polynomials just require adding and multiplying. So I need my function. And let's do this centered at 0. So the function at 0 is 1. And then I need the first derivative. So we already know the general form. I don't need to do anything with the polynomial just yet. We'll use these Maclaurin and Taylor polynomials. I just need to go through and get the first couple derivatives at 0. So second derivative is negative cosine. Negative cosine of 0 is going to be negative 1. Third derivative the fourth derivative at 0. So it's these derivative values that are going to then be the numerators of my Maclaurin series. And there's all those coefficients. Again, I don't write out the 0 factorial and the 1 factorial for the first two because they're so easy. But you can if you want to get into that habit. There, again, do this one last time. There is an x to the 0 for this first one over 0 factorial. And this is technically x to the first over 1 factorial. Same thing. And then I get all of these terms. Here's my coefficients from the derivatives. But then I also need these factorials. And if you notice, I've got a whole bunch of 0 terms there, so they're going to drop out. So here's my polynomial approximation, at least up to x to the 10th. I mean, you can start to see the pattern here, the plus minus plus minus. And so this is for the cosine function. And some calculators use these Taylor polynomials to evaluate trig functions because you don't need to be accurate out to too many decimal places, and this will start to get pretty accurate pretty quickly as you add more and more terms to it. So make sure we get this down. So this is the Maclaurin series for cosine of x, centering at 0 for a Maclaurin series. Also, if you look carefully, these are all even factorials and even powers. What's function that has all these even powers would then be a function that's we considered even. And what do even functions have graphically? Well, they are symmetric to the y-axis. And sure enough, the cosine function itself is also symmetric to the y-axis. So it's not a surprise. So what happens here? Let's actually see what physically happens here. Here's my cosine function. So let's just take these partial sums. Let's just take 1. Well, that's a horrible approximation to the cosine function. It's only good super duper duper close to x equals 0. So let's add the quadratic term. So now this blue function is now the first two functions, this upside down negative x squared quadratic. Okay, that gets a little bit better. Now it's deceiving. They're again only touching at that one point at 0, 1. Well, let's get a little further. Add the quartic term. Ooh, the quartic adds 2 more turning points. Ooh, it's getting better and better. Notice how as I keep adding more terms, this keeps getting wider and wider and wider. And what happens with this particular function, the cosine function, is if you could actually write the infinite number of terms in this polynomial, it would actually approach the full cosine function. So we really don't have to do a lot of shifting for the cosine function because more terms that you add, the wider it's going to be. So it doesn't take very many polynomial terms to actually get pretty far out. I'm actually up to x to the 10th and I'm almost to 1 period. Remember 6.28 is 1 typical cycle. So that's not horribly bad out to that 10th power. So more terms gives us that open interval of convergence. So what if I wanted a cosine of 2x? Well, instead of starting all over again, all I did to the function was replace all the x with 2x's. So I'm going to take that Taylor or Maclaurin polynomial and replace all the x's with a 2x. Now, yeah, that's going to change what some of these coefficients are, but then this would be the polynomial approximation for the cosine of 2x. It's really that easy. Where it gets a little bit different that we have to do something with is if I wanted to be centered somewhere else. So now let's say I want to center it at pi over 2. So now what I'm going to have to do is go through what I did before, but instead of taking all these derivatives at 0, I'm going to go through and take all the derivatives at pi over 2. So the function of pi over 2, cosine of pi over 2, think of the cosine curve as 0. So negative sine of pi over 2, so that's negative 1. And so on and so forth. If you want to pause me here, maybe if you pause, keep going through, maybe get to the 4th or 5th derivatives at pi over 2 and see if you can build a polynomial. Be careful here, we're building a Taylor polynomial, not a Maclaurin, because we're not centered at 0 anymore. So up to maybe 4 derivatives here. So then I'm going to put those in. But remember, these are now, I'm pulling these derivative values. Those are going to go over my factorials. Got my powers matching my factorials. But then instead of x, it's got to be x minus 2 to represent that shift that we made of shifting the graph to the right 2. So if I maybe simplify this expression, here would be the cosine function. It's a polynomial approximation centered at pi over 2. So if I was trying to figure out the cosine of any angles really close to pi over 2, I would maybe want to use this approximation instead. Is this worthy of memorizing? No, because this one we can simply build. The cosine function itself we'll want to memorize. All right, so we got one Maclaurin series down. We'll take a look at a couple more in the next coming days here. But just one more thing to keep in mind, there's just some vocabulary here. So when we're talking about Taylor polynomials, we talk about three things typically: the number of terms, the order, and the degree. So for this cosine polynomial approximation, this particular one, this is a polynomial that has 3 terms. Terms are separated by addition and subtraction. That's something we've been talking about for years. This is the word term. It's a 4th order Taylor polynomial because we use the 4th derivative to get to it. So the order is the number of derivatives that it took to get that polynomial. It's also a 4th degree polynomial because it was raised to the 4th power. So degree is the highest power in that polynomial. That you've known for years. Quadratics are of degree 2, cubics are of degree 3. But be careful with trig functions, it's a little tricky because of all those zeros terms that canceled out in that cosine. We'll see that happen with the sine function here coming up. So this cosine of just these 2-termed expression, this 2-term polynomial, it's also a 3rd order polynomial because that 3rd derivative would have gone to 0, but it turns out to be a degree of 2. You can also consider saying that it's a degree, 2nd order, as well, that we could have stopped at the 2nd derivative and got this as well. So it's trig functions, it's a little bit tricky because of those zeros happening. But again, order is the number of derivatives and degree is the number, highest power. Term is physically the number of terms themselves. I only say this because there was a couple recent AP exams that did mention things about orders versus degrees. Okay, I'm going to ask you to be doing these couple problems in class. We're going to be trying these first 2, at least for now, but make sure that you're at least trying some of these starting problems here. We're going to be working over these for the next couple days here. All right, good luck.